This video is all about the directional derivative and the gradient vector, two important concepts that are connected with one another. We'll start with the directional derivative. And in doing so, we'll first talk partial derivatives. The partial derivatives of a function define the rate of change of the function in the direction of the positive x and y axes. So our partial with respect to x and partial with respect to y gave us two rates of change in only two directions, in the positive x direction or the positive y direction. But from a given point, we can go in an infinite number of directions. So the directional derivative will allow us to find the slope of a surface in the direction of any vector lying in the xy plane. And just to highlight there, any vector. So the directional derivative now gives us a tool to find the rate of change of a function in any direction that we want to go from a given point. The important piece to note is that the vector is in the xy plane. So it's a two-dimensional direction vector that will help us find the rate of change of the three-dimensional function. A good way to think of this is going on a hike. We're hiking in 3 dimensions, and we're using a compass, which gives us a two-dimensional direction vector, or think of it as a two-dimensional direction vector, as we walk along our hike. And as we go, the elevation will be increasing or decreasing. That would be the rate of change as we go in specific directions. Right? So that's a good analogy to think about when we're talking about the directional derivative. There is a limit definition of the directional derivative. We're going to skip that, instead look at it in a different way that will help us more computationally. To find the derivative of the function z equals f of xy at the point x0, y0 in the direction of the unit vector u being u1, u2 in the xy plane, we compute the slope of the tangent line to the cross-section of the surface above the line through the point x0, y0 parallel to u. So there's a lot happening there. So let's draw a diagram out to break this down so we can better understand what exactly this is talking about. So I'll move myself over here. So first let's sketch a surface in. So we'll keep the surface simple. And I want the surface to be black just so I can use other colors to mark it up. Okay, so there's our surface, z equals f of xy. And we have our x, our y, and our z axes. So there's a point that we're trying to compute the derivative at. So let's say it's the point right there, and we'll label that as x0, y0. And there'll be a point on the surface, x0, y0, z0, where we have the output. And then they're going to give us a direction that we want to move in. So let's say the direction is that. Now, important to note, it's a unit vector that indicates the direction, and that's going to be important as we move throughout this video. Then when we're talking about the direction we're moving in, we always want to do so with a unit vector. And the reason is the magnitude is 1. Really, we're looking for the rate of change of the function as we move 1 unit in any given direction. Okay, so now what we can do is we can draw a line through the point parallel to that unit vector. So there's our line L. And that line would give us a cross section on our surface. And we want to find the slope of the tangent line to that point on that cross section. Okay, so the diagram gives us a visual of what we're doing. But how are we actually going to compute what we just drew out? So the first thing that we need to do is define the line. So the line L, we know how to write the equation of a line. It goes through the point x0, y0, and the direction vector is parallel to u. So we'll just use u as the direction vector. So parametrically, x would be equal to x0 plus tu1, and y would be equal to y0 plus tu2. u2. Okay, so now if we combine the line with the function, that creates the cross-section. And if we go one step further, that means that z is a function of x and y, where x and y are now functions of t. Well, that sets up really well to use the chain rule. To diagram this out, z was a function of x and y are now defined in terms of t. And that's what gives us the cross-section. So now, let's do a little differentiating. So dz dt equals partial of z with respect to x dx dt plus the partial of z with respect to y dy dt. And that's all by the chain rule. Okay, so again, on the cross-section, we had the surface, which was a function of x and y, and then x and y became functions of t. That allowed us to expand the derivative that we're looking for with the chain rule. Now let's put in the notation that we're going to see more frequently. So dz dt is not the notation we'll see. It's going to be d subscript of u, the vector u, of the function at x naught, y naught. So we talked about the notation of capital D with our partial derivatives, yet we never actually used it. So here is our first instance where we will use capital D to indicate a partial derivative. In this case, it is the directional derivative. U is the direction we're going in. That will be the subscript. F is our function. We're evaluating it at the point x naught, y naught. So partial of z with respect to x, let's use subscript notation, just as a little cleaner. So partial with respect to x at x naught, y naught. And then dx dt, if we differentiate our x equation with respect to t, we get u1. And then partial with respect to y at x naught, y naught. And differentiate y with respect to t, we get u2. So this is the actual computational approach we will take to find the directional derivative. We're going to multiply the partial with respect to x, evaluated at the point, by the x component of the unit direction vector, and the partial with respect to y, evaluated at the point, times the y component of the unit direction vector. So now that we have a formula, let's actually do a directional derivative. Okay, so find the directional derivative of the function f of xy equals e to the xy at the point 1, 2 in the direction of the vector 3i minus 4j. So there are a few different pieces that we're going to have to find before we put them together to find the directional derivative. Okay, so let's start with our partials. So partial with respect to x is going to be e to the xy times y, and partial with respect to y is going to be e to the xy times x. Evaluate those at the point 1, 2. So we get 2e squared and e squared. Okay, so now we have the values of the partial derivatives. Next, we need to look at the direction vector. And if we remember, we want must be a unit vector, which if we look at the vector 3i minus 4j, pretty quickly we can see that that is not a unit vector. The magnitude of that vector is the square root of 3 squared plus negative 4 squared. Square root of 25 is 5. But we have learned how to find a unit vector. We divide the vector by its magnitude. So direction, the unit direction vector, and I'll use vector brackets instead of i's and j's, will be 3/5, negative 4/5. So our directional derivative, in the direction of u of the function at the point 1, 2 is going to be equal to 2e squared times the x component of that unit direction vector plus e squared times negative 4/5. So that's 6e squared over 5 minus 4e squared over 5. We get 2e squared over 5. And what this gives us is the rate of change of the function, so how the function's output is changing if we move in 1 unit in this direction. Okay, so if we go down this unit direction vector, the function's value will have increased by 2e squared over 5. And that is our rate of change, that is our directional derivative. Now, we often think of the directional derivative more as a dot product than this memorized formula. In order to do that, we have to define another vector, which is the gradient vector. So given a function f of x, y, the gradient of f, and we can even say the gradient vector of f is, here's our notation, okay, so gradient of the function f of x, y. This symbol is called nabla. We never use that for pronunciation. We're going to pronounce this as the gradient or the grad of the function f of x, y. And it's a vector that is made up of the partial derivatives. So partial with respect to x and partial with respect to y. And we can also write this out with I and j notation, but I think vector brackets are sufficient here. If we have a function of 3 variables, then the gradient vector is partial with respect to x, partial with respect to y, and partial with respect to z. So really, the gradient vector is organizing all of the first order partial derivatives in the form of a vector. And the gradient vector tells us a lot, and it's going to be really useful in different areas of this course. But right now, we're just focused on the directional derivative. So redefining the directional derivative, which we established was partial with respect to x times u1, partial with respect to y times u2. Well, the two partial derivatives can be reorganized into the form of a vector. And then u1 and u2 were also a vector, the unit direction vector. And the way that we would get this formula, the sum, would be by taking a dot product, right? It's the product of the like components, and we sum all of those up. And if we wanted to write it even more concisely, we could say that this is the gradient of f dotted with the unit direction vector u. Again, just really for emphasis here, this is a unit direction vector. Okay, we want to ensure that the direction vector is a unit vector before we do any of our directional derivative computations. Okay, so find the directional derivative of the function natural log of x plus 2y plus 3z at the point 2, 1, 1 in the direction of vector v being I minus j plus k. So find the gradient vector. So our gradient vector now, because it's of 3 variables, just a reminder, is going to be partial with respect to x, partial with respect to y, partial with respect to z. Find the unit direction vector, and then take the dot product. So this is a good opportunity for you to pause and see how you're understanding directional derivatives so far. Okay, so I took that opportunity to write out all of the work. Hopefully you gave this a good shot. So check your work. So you should have found the gradient vector to be 1 over x plus 2y plus 3z, 2 over x plus 2y plus 3z, 3 over x plus 2y plus 3z. Evaluated at the point 2, 1, 1 would give us 1, 7, 2, 7, 3 sevenths. The magnitude of the vector v was square root of 3, so the unit direction vector is 1 over square root of 3, negative 1 over square root of 3, 1 over square root of 3. And then the directional derivative, we're going to take the dot product of the gradient vector with the unit direction vector. So 1 over 7 square root of 3 minus 2 over 7 square root of 3 plus 3 over 7 square root of 3 gives us a final answer of 2 over 7 square root of 3 as our rate of change. Our next example, find the directional derivative of the function 2x times x plus y to the third at the point 2, negative 1 in the direction of a vector which forms an angle of theta equals pi over 4 with the positive x-axis. So a little different setup. where they're defining the angle for the direction vector, not the actual components. So we have to break that down a little bit further to get it in the form of a vector. And let's start with that. So if we think of the xy plane, we have this unit vector, so magnitude of 1, where this angle is pi over 4. So if we complete the right triangle, that will give us our two components, right? Our x component and our y component of the unit vector. And the way that we would find that is by taking the cosine of pi over 4 and the sine of pi over 4, since the magnitude or the length of that vector is 1. So we can create a vector of cosine pi over 4, sine pi over 4 to use as our direction vector. So that's going to be square root of 2 over 2, square root of 2 over 2. And the nice part about this vector is it will be a unit vector. Cos squared plus sine squared is equal to 1. And we can check it with the value square root of 2 over 2 as well. So now we have our unit direction vector. We need to find our gradient vector. So the gradient vector of the function. So x requires the product rule, so 2x plus y to the third plus 2x times chain rule 3x plus y squared times the derivative with respect to x is 1. And then with respect to y, just the chain rule, so 3x plus y squared times 1. So there's our gradient vector. Evaluating it at the point 2, negative 1. So 2 minus 1 is 1, which is convenient. So 1 cubed is 1. So we get 2 plus 2 times 2 is 4, times 3 is 12, times 1 squared is 12. And then 2 times 2 is 4, times 3 is 12, times 1 squared is also 12. So our gradient vector is 14, 12. So the directional derivative in the direction of u of the function at the point 2, negative 1 is 14, 12 dotted with square root of 2 over 2, square root of 2 over 2. So we get 7 square root of 2 plus 6 square root of 2, 13 square root of 2 is the rate of change of the function at the point in the direction of u. And just a reminder, there are an infinite number of directions we can go at a given point and an infinite number of points that we can use on every surface. So there is a large number of directional derivatives that we could find even just for this function. And just to summarize something that came up in this problem, the vector cos theta sine theta will always be a unit vector. And that's because cos squared plus sine squared will always be equal to 1. So that is convenient if they define an angle for the direction as opposed to vector components. We create the vector components by using cosine and sine, and it will give us a unit vector right away. So now let's dive a little bit deeper into the directional derivative the way it's defined. So since the directional derivative can be written as a dot product, we can also define it as. So if you remember from our work with the dot product, we had the computational way that we've been using. So find the products of the like components and add them together. And then we had a second way to define the dot product in terms of the angle between the two vectors. So we can say that the directional derivative is equivalent to the magnitude of the gradient times the magnitude of the unit vector times cosine theta. And just to point out, theta is the angle between the gradient and u. And we can even go one step further because we are using a unit direction vector. That magnitude should be 1. So we can reduce this to the gradient of the function times cosine theta. Now, where is this beneficial? Computationally, we're often going to use the dot product the way that we have been doing up to this point in the video by finding the gradient vector, finding the unit direction vector, and doing the dot product. But this way of defining the directional derivative in terms of the angle between the two vectors will allow us to talk about some properties of the directional derivative, right? If we think about cosine theta is between -1 and 1, which means that this expression can have the largest value possible of the magnitude of the gradient vector times 1, and the minimum value would be when cosine would be -1, and that would be the negation of the gradient. Now, ultimately, what does that mean? That means at a given point, the maximum value of the rate of change in any direction is equivalent to the magnitude of the gradient evaluated at that point, since the largest value you're going to get for cosine is going to be 1. And the same argument can be made for the minimum rate of change. Take a point. If you're walking in any direction from the point, remember there's an infinite number of those, the lowest rate of change that you're going to find is the negation of the magnitude of the gradient, because the lowest is cosine, lowest value of cosine is -1. So let's formalize this into some notes. So the maximum value of the directional derivative at a point is the magnitude of the gradient at that point, and it occurs in the direction of the gradient vector at the point. Now, a little bit harder to wrap your head around this, but if we think about it, we said the maximum happens when cosine is 1. Cosine is 1 when theta equals 0. Right? So here the assumption is the angle between the two vectors is 0, which means we would want to pick a unit direction vector that's some scalar of the gradient vector. Okay? They don't have to be the same vector, so to speak, but they need to go in the same direction so that the angle between them is 0. That's what would give us the maximum rate of change. And then for the minimum rate of change, it's the negation of the gradient vector at the point, and it occurs in the opposite direction of the gradient. And that's because we're using cosine to be -1, which means theta would be equal to pi. So the angle between the two vectors has to be pi. Again, they don't have to be the exact same vector. Okay, so let's say the gradient vector is 1, 1. We don't need the unit direction vector to be -1, -1. We could pick a unit direction vector in that direction. And then two other properties of the gradient vector that we'll dive a little deeper in as well is the gradient vector at a point is orthogonal to the level curve of the function through that point. And the same could be true if we have a function of 3 variables. The gradient is orthogonal to the level surface of the function through the point. This last bullet, we're going to dive a little bit deeper when we talk about tangent planes, but this third bullet with the gradient is something that we're going to look at on the next slide because it's an important trait of the gradient vector that can be a little bit hard to understand. So let's focus on the fact that the gradient vector is orthogonal to a level curve at any point on the level curve, and showing why is that true. So to show that the gradient at a point, x0, y0, is orthogonal to the level curves of the function, choose a unit direction vector u that keeps you on the level curve at that point. Okay, so here we have a set of level curves. So at this point, just to show you, the gradient vector is going to look something like this. The exact length we're estimating, okay, could be longer, could be a little shorter, but the one thing I want you to notice is it's pointing in the maximum rate of change. That circle that we're on is k equals 1. The next circle would be k equals 2. The one after that, k equals 3. So we're pointing in the direction where the outputs of the function go up. And remember, the labels of the level curves are the outputs of the function. So then it said to choose a direction vector. So choose a direction vector that keeps you on the level curve. So pick a direction vector that is tangent to the curve. That will keep us on the curve by that point. Now, why is that important? Well, if we're staying on the curve, and this one is k equals 1, that means the function output will also be 1, right? So at the point we're at, output's 1, we move a little bit on the curve, the function output's still 1. What is a directional derivative? It's the rate of change of the function in a certain direction. Well, if we stay on the level curve, the rate of change of the function is 0. The function value is not changing on the level curve, right? F of x naught, y naught stays the same on the level curve. Okay, now on the left side, we know that we can define the directional derivative as a dot product. So that's the gradient of the function at x naught, y naught, dotted with the unit direction vector equaling 0. Okay, so far nothing crazy. Hey, the hardest part is convincing yourself why the directional derivative would need to be 0. Now, once we establish this, what does it mean for the dot product of two vectors to be 0? Well, that means that the gradient at the point is perpendicular or orthogonal to the unit direction vector. And because we didn't use a specific point, we generalize here. We can do this anywhere on the set of level curves, right? If we wanted to draw a gradient vector, let's say right here, we would draw it so that it is orthogonal or makes a right angle with the level curve that we're going from. Okay, I can even put the right angle in there. Okay, so let's look at two more examples to finish off this video as far as directional derivative goes. So determine the maximum value of the directional derivative of the function sine of 2x plus y at the point 0 pi, as well as a unit vector in the direction in which the maximum value occurs. So both of these questions rely on the gradient vector. So that's a good place to start. So the gradient of our function is equal to partial with respect to x is going to be cosine of 2x plus y times 2. And then cosine of 2x plus y times 1. Evaluate the gradient at the point 0 pi. So we have cosine of pi, which is -1 times 2, and then -1. So we get -2, -1. So there's our gradient vector. So now, properties of this gradient vector are going to answer both questions. So the maximum rate of change is going to be the magnitude of the gradient at 0 pi. So that's the square root of -2 squared plus -1 squared, which is the square root of 5. So the maximum rate of change that we can get moving in any direction from the point 0 pi should be the square root of 5. So just so you know, if we got a rate of change of 10, we know we did something wrong because the maximum rate of change that we should be finding is the square root of 5. And the unit direction that we're going to move in, well, we want the direction to match the gradient vector. We want those two vectors to go in the same direction. And we have the magnitude of the gradient, so that's going to be -2 over the square root of 5, -1 over the square root of 5. Okay, let's go through a similar problem, but now talking about minimum rate of change. So now would be a good time to pause the video. I know we're almost towards the end. Pause video, try this, and then play the video to see how you did. Okay, so hopefully you paused the video and were able to work through this problem. Notice it's now talking about the minimum value as opposed to the maximum value. So the gradient of the function is 2xy plus 2 over x squared y, x squared plus 2 over xy squared. Evaluate at the point 1, 1, we get the vector 4, 3. So that's our gradient vector. So the minimum rate of change is the negation of the magnitude of the gradient at the point, so -5. And then the unit direction we would want to move in is the negation of the unit vector in the direction of the gradient. So 4/5, 3/5 is the unit vector in the direction of the gradient. So negating that, -4/5, -3/5. So a lot of small details in this video when we're talking about the directional derivative and the gradient vector. The gradient vector in particular can be challenging to wrap your head around, and we're going to continue to work with it throughout this course. And this is really just an introduction. A maximum rate of change, minimum rate of change, and the direction is important for connecting it with the directional derivative. And the orthogonal piece is something that we're going to build off of and talk more about as we continue through this unit. So get your practice so we get a better understanding, and then I'll see you in the next video.